Ladies and gentlemen, welcome back to Lesson 10 in Group Theory. In this lesson, we're going to be proving two of the theorems that we've seen in the last lesson. These two theorems concern the subject of classifying our cyclic groups and our cyclic subgroups. If you don't know what a cyclic group is, I highly recommend you go back to our previous lesson where we explained the meaning and the interesting results that arose behind cyclic groups. So Theorem 1 will be classifying all of the cyclic groups according to their cardinality. In other words, the number of elements it has will determine completely the nature of the cyclic group. Theorem 2 will be talking about the cyclic subgroups of a cyclic group, and we will find out using the theorem, and we will prove that it is in one-to-one correspondence with the divisors of the order of the group. In other words, if the order of the group was 10, then the subgroups that are possible are the divisors, are ones which have the same number of elements as the divisors of 10, which is 1, 5, 2, and 10. So on the right there, I've drawn these two symbols signifying the first and second theorem. So the first one says that if a cyclic group, such as the cyclic group generated by rotations in D to N, has 3 elements, then it is in one-to-one correspondence with Z3Z, which is the cyclic group of integers modulo 3. So in other words, any cyclic group with 3 elements would be isomorphic to this. And this is what we will be working on proving. And in here, we have that the cyclic group generated by the element 1, let's say this is in modulo 12, so this is in Z12Z. We've seen in the last class that in Z12Z, the cyclic group generated by the residue class 1 will generate the whole group, Z12Z. And this is equal to, in fact, the cyclic group generated by 5, because we've seen one of the results of the theorem says that if the GCD of 1 and 12 is equal to 1, then we can go ahead and say this generates the entire Z12Z. And for 5 as well, it follows that the GCD of 5 and 12 is equal to 1. So 5 and 12 are coprime. So we can say that 5 generates the entire group of Z12Z. And this can apply for any number that is coprime to 12, such as 1, 5, 7, and 11. And you can try that out yourself. Try adding 5 to itself and see if you will get back all of the elements, all of the residue classes mod 12. Let's get started with the proof of these two very important theorems. Okay, now let's start with the statement of the theorem 1, which simply says that any two groups which have equal order, equal cardinality, equal number of elements are isomorphic. And the notation that we will be using from then on will be that a cyclic group with order n will be called Cn or Zn. So we have just classified all the cyclic groups according to how many elements they have. The proof of theorem 1 will be in two parts. The first part I will prove, and the second will be left to you as an exercise because it is very similar to the first part, and it will be a good way for you to practice this sort of proof. This sort of proof is not just particular to this type of theorem. It will be used many times to prove that there is an isomorphism. And the way to do that is by constructing a map and then proving that this map is well defined and that it's a homomorphism and that it's injective and surjective, and therefore we can say that this map between these two groups this map is an isomorphism, therefore the two groups are isomorphic to each other. So I'd like you to practice this way of proving things because isomorphism is a very important property in algebra, not just in group theory, but also other fields of abstract algebra. So let's get started. So the first case is if the group G is finite, then we will write G is equal to G to the R for R being any integer between 1 and n. And G to the n, therefore, would be equal to the identity 1. So this is a finite cyclic group. So now we will construct our map phi. So let phi be the map that takes an element from Z and Z and gives back an element in G. So the element it takes from Z and Z will be a residue class, call it K, and giving us the element G to the power K. So it takes the residue class, it will take the representative K, and it will put it here and give us the kth power of G in the group G. So we will now prove that phi is an isomorphism. Because if we prove that phi is an isomorphism, then this will mean that Z and Z is isomorphic to G for all groups G that are cyclic and finite. So if this is true for all groups G that are cyclic and finite, that means all the groups are isomorphic to this one group, therefore they're isomorphic to each other. So all it takes is to know how many elements are in the group G, which are n elements, and we can say that they are isomorphic to this one group Z and Z. So if H was another group that is cyclic of order n, then H would also be isomorphic to Z and Z. But then since isomorphism is a transitive property, we can say that G is isomorphic to H. And therefore this would prove what we wanted to say here in the theorem, that two cyclic groups of equal order are isomorphic. So let us prove that phi is an isomorphism. To do that, we need to start by prove phi is well defined. To prove that a map is well defined, we need to say that if A is equal to B, then phi of A is equal to phi of B. So if the inputs are the same, then the outputs must be the same as well. So if A bar is equal to B bar, remember we have to put the bar there because that's the input of phi, a residue class in Z and Z. We want to see that phi of A bar is equal to phi of B bar. But phi of A bar is, by definition of phi, G to the A, and phi of B bar is G to the B. So essentially saying we want to say that G to the A is equal to G to the B. So how can we do that? Well, since A bar is equal to B bar, A is congruent to B modulo n, and by definition of being congruent, that means n will divide the difference A minus B. So we have n dividing the difference A minus B. And this means that since n divides A minus B, there exists an integer C such that n times C is equal to A minus B. We will use this relation here in saying that G to the power A minus B is equal to G to the power n times c, and by exponent laws, this is equal to g to the n to the c, and we know that in we know that in g to the n is equal to the identity. So this is equal to the identity. So this is identity to the power c, which is equal to the identity. And we know that g to the a minus b is equal to g to the a, g to the minus b by exponent laws. And if we multiply both sides of the equation by g to the b, we will have that g to the a times the identity is equal to the identity times g to the b, and this gives us that g to the a is equal to g to the b, therefore proving that phi is a well-defined map. Let us now prove that phi is a homomorphism. We will use the definition right away to say that phi of a bar plus b bar is equal to phi of a plus b bar by a property of modular arithmetic, and this equals to, by definition of phi, g to the a plus b, and we use the exponent laws here to say this is equal to g to the a times g to the b, but g to the a is equal to phi of a, well, phi of a bar, and g to the b is phi of b bar. So phi is a homomorphism. We now prove that phi is injective. So if phi is injective, we want to use the fact that because of a property we've seen before where injective is in double implication with the kernel of phi being equal just to the identity. So we want to show that the kernel is just the identity. So phi of a is equal to the identity if and only if g to the a is equal to the identity, because that is just the definition of phi, isn't it? So when is g to the a equal to the identity? Well, g to the a is equal to the identity if n divides a, and n divides a, meaning that a bar is equal to 0, and 0 is the additive identity of z and z. So we concluded that if phi of a bar is equal to the identity, then a bar necessarily is equal to 0. And if a is equal to 0, well, of course, we have that phi of 0 is equal to the identity. Therefore, saying that the kernel of phi is exactly the identity, which is, well, 0 bar in z and z. Therefore, saying that phi is injective. And lastly, we say that phi is surjective because if for any element in G, we would have it in the form g to the power h for some integer h between 1 and n, and it would be in G, then g of h would just be equal to phi of h bar, and phi of h bar is in the image of phi. So basically what I just said is that any element in the cyclic group G has the form g to the h, but we know that g to the h is the image of some h bar by phi, thereby proving that phi is a surjective map. So we have that phi is a well-defined homomorphism that is both injective and surjective, so phi is an isomorphism, thereby proving the result for a finite cyclic group G. Now, for the infinite cyclic group, if G is infinite, we will let G to be equal to G to the R, where R is any integer that we want. And to give you a hint to how to proceed, the construction of phi will be going from all the integers z, not z and z, all of the integers, to the group G, giving the same exact construction where the integer is mapped to the kth power of G. So it is to you now to prove that phi is an isomorphism, and having done that, you will have proved the infinite case. And this terminates the proof of this theorem. Let us now state theorem 2 again. So if G is a cyclic group generated by small g, then first of all, every subgroup H of G is either the trivial subgroup containing the identity, or H is equal to the subgroup generated by G to the D, where G to the D is not equal to the identity. The second result says that if G has infinite order and A and B are two distinct natural numbers, then the group generated by G to the A is not equal to the group generated by G to the D. Thirdly, we have that if G is a finite group with order n, then for all positive integers A that divide n, we have a single subgroup H such that the order of H is equal to A, and moreover, the construction of H is such that H is equal to the group generated by G to the D, where D is equal to n over A. Let's get down to the proof. The proof of the first part of the theorem will use several techniques, and I will be explaining each of these techniques in turn when we arrive at them. The first technique is to simply discard the trivial case. So the trivial case is that H is equal to the set containing only the identity. So if H is equal to that, then we're done. If H is not equal to that, then we will have to prove that H is the other option. So, writing it formally, we have suppose that H is a subgroup of G if H contains only the identity element, then we're done. There is nothing to prove. The theorem said is either H is this or H is that. Okay, so if H is this, we're done. If not, if H is not equal to the set containing the identity, we want to prove that H is equal to the group generated by G to the D, where G to the D is not equal to the identity. So to do that, we will perform a certain construction. Let K be equal to all the positive integers small k such that G to the K lies inside H. So it is all the positive integers where G to the power of that integer gives you an element in K. We know that this set K is non-empty because we've just said that since H is not just the set containing the identity, it contains another element which has to be G to the K, where K is positive, because remember, we are in a cyclic group. So in a cyclic group, every element is the power of the generator here. Every element is G to the K for some K. So K is non-empty. And now I will tell you another technique of proving things, which is called the well-ordered principle, which says that if the set is non-empty, then we can find the smallest element in the set. So by the well-ordering principle, there exists a minimal d in K, so the smallest integer d in K, because all the integers here are positive, so there has to exist a smallest one. Okay, we clearly see that G to the D, so this is the group generated by G to the D, and since D is inside K, that means G to the D is in H. So we know that g to the d lies in H, but then since H is a subgroup, we have to have that subgroups are closed under operation of the group and closed under inverses. So any multiples of g to the d has to be inside H as well. So that means that all the generation of g to the d has to be a subgroup, has to be a subset of H for that reason. Okay, so we want to prove that any element in H now is a subset of the group generated by g to the d. So let g to the a be in H for some a that we don't know of. A is equal to dq plus r. This is another technique in proving things. This is called the division algorithm. The division algorithm states that any number can be written into d times q plus a remainder r. And we've seen this in elementary school. We're just applying it here. So g to the a would be equal to g to the dq plus r. And by exponent laws, this is equal to g to the dq times g to the r. And now if you multiply both sides of the equation by g to the minus dq, what we get is that g to the minus dq times g to the a, both of these elements lie in H because this lies in H by supposition, and this lies in H because g to the d lies in H by the construction of d. And this is equal to, these two will cancel out because cyclic group is commutative, so it's going to be just g to the r. So because this element here is in H and it's equal to this element, that means g to the r must be in H. So in the division algorithm, when we say that a is equal to dq plus r, the thing about the division algorithm is that r has to be strictly less than d. So r is strictly less than d. But here we've just said that g to the r is an element in H. So this means that r is an element in K. It is one of those integers, k, such that g to the k is an element in H. But we've just supposed that by the well-ordering principle, d is the minimal element in K, the smallest element. And we've just found out that there is an r in K such that r is less than d. So that means d is not the minimal element in K. So we are saying at the same time that d is a minimal element and that d is not the minimal element in K, which obviously is a contradiction because they are contradicting facts. So this leaves us to see that either r is less than d or r is equal to 0. So the other option is for r to be equal to 0, and if r is 0, then it's a is equal to d times q. So a is equal to d times q, and this means that g to the power of a, which is in H, g to the power of a, which is in H, is equal to g to the power dq, but g to the power dq is equal to g to the d to the q. So it is a power of g to the d, and we've said that this element lies in the group generated by g to the d because this group contains all of the powers of g to the d. So we've just proven that if an element is in H, therefore it is in this group, And so this means that H is a subset of this group. Therefore, we have proven that these two facts, this one and this one here, we've proven that H is equal to the group generated by G to the D by the double inclusion property. So this terminates the first part of the proof. So to prove the second part of this property, we're going to be using what is called the contrapositive of the statement. So the contrapositive will assume the opposite of this, and we will reach that A is equal to B, because this is a very popular thing in proving things. So P implying Q is the same as saying not Q implying not P. So just assume the opposite of Q and reach the conclusion, which is the opposite of P, and those two implications are equivalent. So we would have that, okay, let G be an infinite cyclic group and assume the opposite of this. Assume that the group generated by G to the A is equal to the group generated by G to the B. So we assume this and we want to reach that A is equal to B. So here we're going to be using a technique that we've already used to prove a similar result in last class, assuming that, of course, the order of G is infinite. If the order of G is infinite and G is a cyclic group, that means that if we have G to some K is equal to the identity, then K cannot be a positive number, because if it were, then the order of G as a group would not be infinite anymore. So K has to be equal to 0 if we have G to the K is equal to the identity. So if we have this, then we can say that an element here is a power of G to the B, and an element there is a power of G to the A. So we can say that G to the A in particular is equal to G to the B to the K for some integer K. Okay, so that is true because we're assuming these two groups are equal. So this is equal to G to the B times K by exponent laws. And now we're gonna move this to the other side of the equation to have G to the A minus BK is equal to the identity element. What I mean by moving it to the other side is just multiplying by the inverse on both sides, basically performing some algebra. So I have this now. And remember what I said, if G to some power gives the identity in an infinite group, then we should have that A minus BK is equal to 0. So this implies that A minus BK is equal to 0, which implies that A is equal to BK. So this implies that B divides A. Okay, we can use the same argument by taking an element from which is G to the B and saying that it's a power of G to the A. So if you using the same argument, we can arrive at a similar conclusion, except that the roles of B and A would be reversed. So we would arrive at A divides B. And in number theory, if two numbers divide the other, then we conclude that A is equal to B or A is equal to minus B. These are the only two possibilities if B divides A and A divides B. You can check it out for yourself. So imagine we have 5 divides 5, but also minus 5 divides 5. Because minus 5 times minus 1 is equal to 5. So minus 5 divides 5, and 5 divides minus 5. Okay? So we have these two possibilities, except that this possibility in this case is not possible because we've assumed a and b to be natural numbers. In other words, both a and b are bigger than 0. So if a is bigger than 0 and negative b would be less than 0, that would be a contradiction. So we should have that both a and b are equal. Therefore, proving the contrapositive of this statement and terminating the second part of the proof. To prove the last part of the theorem, we will use proposition 3, which we have seen in lesson 10. So here we will suppose G be a finite group of order n, a cyclic group, and A dividing n, where A is positive. So A is some positive integer that divides n, and D be equal to n over A. Okay, so here we use proposition 3 in lesson 10. If you don't know what that is, I strongly recommend you hop on the playlist and click on lesson 10 to know more about this proposition. So in proposition 3 in lesson 10, I have that there exists an H, a subgroup of G, such that H is equal to the group generated by G to the D, and the order of H is equal to n over D. But D is equal to n over A, so it's n over A, and that is equal to A. So we have just proven that there is an H that is a subgroup of G such that the order of H is A, and that H has this form where D is equal to n over A. So all of that has been proven now. The only thing that's left to prove is that this is the unique subgroup with this property. In other words, there is no other different subgroup that has these properties. So, prove H is unique. To do that, we will suppose that there is another subgroup. There exists an H1 that is a subgroup of G, such that the order of H1 is also equal to A. Then we can say that H1 is equal to G to the B by the same argument using proposition 3, and that A is equal to the order of the generating element, because the order of the group equals the order of its generating element, as we've seen in proposition 1 in lesson 10. So we have this, and the order of G to the B is equal to, by proposition 3, n divided by the GCD of n and b. Again, we have proven all these results that I'm talking about here. Since we know that A is equal to n over D, all we gotta do is replace A by n over D, and we have that n over D is equal to n over the GCD of n and b. So this means that D is equal to the GCD of n and b. But D being the GCD of n and b means that but now D is the greatest common factor of n and b, so in particular D divides n and D divides b. So if D divides b, then this means that G to the b must be an element in the group generated by G to the D. Because remember, this group is equal to G to the D times K for all integers K. So because D divides B, then b is equal to dk for some integer k, and that's exactly what we're saying here. B is equal to dk. So we have that g to the b is an element in the group generated by g to the d. So we've successfully proven that any element in H1 will be contained in H, since the generating element is found in H. So this is a very nice property. Because H is a subgroup, we have that it only suffices to prove that the generating element lies in H. And this is sufficient using the property of being closed under the group operation and inverses to say that the whole subgroup H1 is a subset of H. Very cool. So now the only thing left for us to prove that H1 is equal to H. So right now we know that H1 is inside H, like that. We don't know if they're equal to each other or not. We just know it's contained inside. But just remember here that the order of H was supposed to be A. Well, we've said that there exists an H with order A, and now we've just supposed that H1 also contained A elements. So this leads us to see that the order of H is equal to the order of H1. So they have the same number of elements. So if we have two sets, one a subset of the other, and they have the same number of elements, then we're forced to conclude that the sets are equal. So this means that because any group with this property is equal to a single group H, this H must be unique. So this means that H is unique. And this terminates all three parts of the theorem 2, and this is the last thing that we wanted to prove in this lesson. If you've liked, I hope you will enjoy the future videos that I'll be posting. Please like and subscribe for more content, and share with anyone who would be interested in this magnificent subject. I'll see you on the next time. Have a nice day, and bye.